This project presents a comprehensive analysis and medium-term forecast of a province's retail sales tax revenue. It outlines the statistical and econometric techniques used to estimate revenues, drawing on historical data and forecasted economic indicators. The primary objective is to project tax revenue estimates for inclusion in the budget and quarterly fiscal updates. The dataset comprises a time series of retail sales tax revenue from 1987 to 2023, along with a forecast database extending to 2029. The goal is to produce accurate and reliable forecasts for the years 2024 to 2029. I start by importing the data from a CSV file into a Pandas data frame. The variable names are located in the second row, while the descriptions of each variable are in the first row. First, let's generate a list of variable names along with their corresponding labels. Then, I reset the data frame to use the second row as the proper column headers, and remove the first two rows since they're just header information. Next, I clean the data. I apply pd.toNumeric to every column to convert all data points to numbers, setting errors equals coerce, so any non-numeric entries become nan. This ensures all variables are numeric for analysis. Many variables in the dataset are quite similar to each other and are therefore highly correlated. To address this, we rely on economic theories to identify and select the most important determinants of sales tax revenue. I then use describe to get summary statistics, minimums, maximums, means, standard deviations, which helps verify that the data is reasonable and highlights any missing or extreme values that might need attention later. Here is the list of 10 variables in the clean dataset. Tax revenue is the dependent variable, and the rest are independent variables. Because tax revenue and other economic variables are reported in nominal terms, which includes inflation, I adjust them to real terms. I divide each nominal variable by the CPI series, converting them into inflation-adjusted values. This step is essential so the relationships between revenue and predictors reflect actual economic activity, not just price changes over time. I split the data into a training set from 1987 to 2023, and a forecast period covering 2024 to 2029. This split mirrors the real-world scenario of using historical data to predict future revenue. Then, I prepare my feature matrix X with the real predictors and set my target variable Y as the real sales tax revenue. Before modeling, I use standard scalar from sklearn to standardize all features to zero mean and unit variance, which improves model stability and performance, especially for regularized regression models. Lasso and ridge regression models are chosen as the primary modeling technique due to its robustness against multicollinearity, effectively stabilizing coefficient estimates. I begin modeling with lasso regression, which uses L1 regularization to shrink less important coefficients to zero, effectively performing feature selection. After fitting the model on the training data, I use it to predict real tax revenue for 2024 to 2029. I multiply the predicted real tax by the forecasted CPI to convert it back to nominal terms. And here is the predicted nominal tax series. I then plot the actual historical tax revenue alongside the lasso forecast to visually assess how well the model extends trends into the future. Next, I train a ridge regression model, which applies L2 regularization to control coefficient sizes without zeroing them out completely. Like before, I predict future real revenue, adjust it with CPI, and plot it with actual data to compare how ridge forecasts differ from lasso. ElasticNet method combines L1 and L2 regularization, offering a balance between lasso and ridge. After training it on the historical period, I forecast 2024-2029 real tax revenue, back transform with CPI, and plot the ElasticNet forecast against actual revenue to see its performance. In section 4.4. To capture potential nonlinear relationships, I built a pipeline combining polynomial features and ElasticNet regression, optimized using grid search CV. Polynomial features generate squared, cubic, and interaction terms between predictors, allowing the model to explore nonlinear patterns in the data. Grid Search CV systematically searches combinations of polynomial degrees, alpha values, and L1 gradation parameters to find the best hyperparameters by cross-validation. The optimal configuration was polynomial degree 1, alpha 0.001, and L1 ratio 0.9. After fitting the pipeline, I forecasted future real revenue, converted forecasts back to nominal terms, and plotted the results to assess whether incorporating nonlinear features improves the model's ability to capture complex trends. Finally, I evaluate model performance by calculating the in-sample R-squared for each model on the training data: lasso, ridge, elastic net, and polynomial elastic net. I display them in a table to directly compare which model explains the most historical variance, providing an evidence-based choice for the most reliable forecast. That concludes my provincial sales tax forecasting project. This work demonstrates end-to-end capabilities in data ingestion, cleaning, real variable preparation, model development, forecasting, and performance evaluation. It highlights expertise in time series data processing, regression modeling, and visualization. Time series forecasting is a powerful example of how data-driven insights can support policymakers in making informed decisions. I welcome the opportunity to discuss how these methods can be tailored to your organization's needs.